Really appreciate it. Thanks to the Vanitech Energy Storage Committee for allowing us to share our work here today. Next slide, please. So at TyFast, what we're building is ultra-fast charging, ultra-long cycle life batteries based on vanadium oxide for the anode side. So back to Mikhail's earlier question, could we use vanadium in electric vehicles? The answer is a resounding yes, and not only on the cathode side, but also on the anode side, which is what we're focused on. We're focused on building again truly frictionless charging, untethered experience. Call it devices and platforms. Next slide, please. So graphite is the dominant anode in lithium-ion batteries. It is a highly abundant, low cost, and high energy material. However, it's also fundamentally limited because it's a trickle charge battery. It takes hours to charge a graphite-based anode cell. If you were to charge it fast, you would further impact its short cycle life. And in the worst case scenario, you could actually have heating issues or explosion issues with graphite-based cells if you were to push it too fast when charging, or actually charge it below freezing. So I don't know if you guys have noticed, but you actually do not charge your graphite-based lithium-ion cells at cold temperatures. So next slide. Our solution is a game-changing lithium vanadium oxide anode called LVO. It enables now a 20x faster, 3 minutes fast charging cell, 20,000 full cycles of life, 20x longer lifetime, and also a wider range of charging temperatures and an enhanced safety factor. Next slide, please. Here's how we aim to apply the LVO anode if you do a cross-section of current lithium-ion batteries today. What you'll see here is a cathode, anode, electrolyte, and separator stack. Graphite is the dominant anode in lithium-ion batteries. All we want to do is basically replace the graphite anode with our LVO, lithium vanadium oxide based anode material, and enable those faster charging, longer cycle life batteries. We can pair with a vanadium-based cathode as well, as Dimian had shown, or any other cathode that's out there in the market with high energy and high voltage. Next slide, please. So here's how we know the LVO works. Our company is a spin out of UC San Diego. The material LVO was discovered in 2018. In 2020, was published in the journal Nature. And here are the key properties that makes this material different that allows us breakthrough battery. So the analogy here is, the source code of a piece of software enables its different, call it application space. In the case of batteries, the material properties of the electrode materials enables essentially a different battery performance factor. So for LVO, what we found over the 2-3 years of research done on this fundamental material is that in fact it has faster lithium transport in the crystal structure, enabling this fast charging device or battery. It has also much lower volume expansion as you charge or discharge the cell, enabling a more stable anode structure and a much longer cycle life cell. It operates at 3 times higher voltage versus graphite. So in fast charging modes, you actually don't crash the anode voltage into the lithium plating region, enabling a safer battery. And it also has high capacity, enabling a high energy cell. In our case, approaching 80% of what a graphite-based energy density would be. In our sort of everyday use, that would be, I'll call it 80% of the runtime of what a graphite-based cell, with the trade-off of very fast charging and very long cycle life. Next slide, please. Here's how we compare against the competition, and these are the different anode materials that are out there in the market today. The vertical axis is charging speed, cycle life, and then the horizontal axis is charging speed. Graphite, the existing anode today, is a slow charge material, about an hour or more. Short cycle life material, less than 1,000 cycles. The emerging anode materials that are out there, lithium metal or silicon, are expected to charge faster, but also have very large volumetric expansion, 100% or more as you charge and discharge a cell, resulting in a compromise in the cycle life for these particular batteries. And this is where LVO is different. We're able to deliver 20x faster life, 20x faster charging speed, and also 20x more lifetime. So the key question here is, where would TyFast LVO anodes apply in the market? Next slide, please. So this is where we identified effectively batteries that can charge really, really fast and practically live forever to be impactful in always-on applications. We identify here 3 different areas or different growth stages for applications that we have targeted at TyFast. I'll start with the right-hand side. Towards the end of the decade, we aim to deliver essentially the anode material into commercial and fully autonomous electric vehicles. These vehicles are expected to run basically all the time. Our passenger personal EVs, we maybe drive 1 to 2 hours per day. That's not always on. That's not where a highly impactful application for ultra fast charging and ultra long cycle life could start. Whereas commercial vehicles today run 8, 12, 16 hours or more. When they become fully autonomous, they can basically run 24/7. And this is where an always-on application would be really powerful. Prior to that, areas where there's a significant amount of automation and robotics for industrial and commercial settings, warehouses, factory floors, in fact, are effectively the same application, but just shrunk down and smaller in scale. We believe that's where we can be at mid-decade. These robotics platforms all have wheels. They basically drive around in a factory floor or in a warehouse setting by themselves. And then when they need a quick charge, they drive to a charging station within that essentially floor setting and then get back to work. In the lab today, though, we are building small scale cells the size of a credit card or smaller. And what we found is that, in fact, there's an even earlier market, wearables, AR, VR, or consumer space, things that basically are on our bodies that have very small batteries and could be impacted by effectively always-on application. So think of a smart eyewear. These systems today, if you had them, would only have 2 or 3 hours or 4 hours of essentially runtime per charge. They basically charge for more than an hour, giving a really low hardware usability, especially when there's long charging downtime. What we enable would be a, when you take, let's call it an eye break, you set it down, and after a few minutes, the device is fully charged and fully back on. That's what TyFast enables. Next slide, please. So I'll talk about, sort of for that application, some of the value propositions we've shared with potential customers in the space and what they really like about it. So TyFast effectively gets you back to life faster with these consumer or wearable devices. Compared to a graphite-based anode, we're able to charge more than 10 times faster, enabling, again, always-on applications. From a cycle life standpoint, 20,000 cycles is effectively unlimited use. It's on all the time, and you can cycle and not worry about capacity fade or performance fade out of their battery. In addition, you can effectively have an all-weather battery, charge and discharge across all temperatures, low and high. The one trade-off, obviously, as with all batteries, would be in our case is the runtime. So we are not the battery for, I'll call it marathon long applications, where the battery that effectively reduces critical downtime issues and allows for always-on applications. Next slide, please. We've spoken to many customers in the space. World leader in wearable devices, and possibly some of you guys are wearing their devices today, has basically told us that our fast charging approach, which is really different from where the market is going, is really promising and can be a game changer. In fact, the need for fast charge is already here. They're pushing graphite-based cells to charge faster at the expense of even shorter life. And in some cases, what they're trying to do is effectively increase the battery size with smaller and smaller wearables that are packing more and more sensors and have higher and higher, call it device loads. You can't really, engineer your way to larger batteries when your devices are getting smaller. And this is where TyFast and the LVO anode can make a difference. Next slide, please. Our business model is to directly sell batteries, in fact, to this launch market. We want to use contract manufacturing to enable essentially assembly of our batteries that contain our LVO anode, which is a drop-in replacement for graphite. Use your standard high-energy cathode or whatever cathode is utilized in these different markets. Typically for smaller wearable devices or even consumer products, everything that's around our house today actually has an LCO or cobalt oxide based cathode. We would be compatible to that. As you get to larger applications, this is where your nickel, manganese, cobalt oxide based cathodes actually now start to supplant. We are compatible with both of those cathode chemistries, and we're also compatible with standard battery assembly. What we would also then do is provide effectively our LVO, either in powder form or full anode electrode form, to that battery assembly maker to essentially drop into their manufacturing process to enable building a TyFast anode containing cell. Next slide, please. So where are we at today? We are building these prototypes, these credit card size cells in our lab. We are testing them. What we've shown is that the anode itself, when paired with a reference electrode, can effectively deliver your 3-minute charging cycle and your 20,000 cycles without any capacity fade. What we're doing is essentially increasing the energy of these prototypes to make them effectively commercially relevant type cells. The goal is to complete these prototypes by the end of the year and provide them to early, call it sample testing for customers in the wearables or small scale application space. Successful completion of that would then allow us to do pilot scale contract manufacturing that now goes from I'll call it a hand-built cell to a semi-automated pilot produced line cell that could scale up and do validation testing with essentially customers, again, in the small form factor battery devices space. Successful completion that could then launch us to full-scale production. Again, using a contract manufacturer to enable us to actually get to market sooner and then do beta testing or early product testing, then to the next markets, industrial, automation, and robotics, and as well as electric vehicle platforms. Next slide. If you guys want to reach out to TyFast, feel free to get to our website and then hit the contact button form, and we're happy to connect with you. Thank you.
Great, thank you, GJ.